So we'll do this in two parts. Leilei will be talking in the second part, doing all the heavy lifting with the technical details. Some of the stuff is actually joint work with Xiangping Jiang and also with Arthur, who's here in the audience, and Milad Siami at Northeastern University. So let me. I don't know. In this audience, I don't know how many people are used to looking at gradient systems. So let me just give you the big, the broad background. So the idea is, suppose that we have some sort of loss or cost function, let me call it L, that you want to minimize on some sort of set, typically an open set. So there's some function L that goes to some D into the reals. This set is typically not convex, and the function L is not a convex function. Let's assume that a minimum exists, and let's take the denote by K underbar the point at which a minimum is achieved, and L underbar the minimum value. Now, I don't need to assume that K is unique for the beginning of what I'm saying. So there could be a whole manifold, say, of points where L is minimized. So to make things, really what motivated me looking at all this was work that was done by many, many people in the context of continuous time linear quadratic control. So back to just very basics. In continuous time linear quadratic control, let me take the simple example of a very complicated system, an integrator, okay? We'll take initial conditions x of 0 equals 1. I'm assuming that I'm in the scalar case. And in that case, of course, the linear quadratic control cost associated to a particular feedback strategy, negative K of S, when I plug in, will be just, because I'm taking Q and R be equal to 1, will be just the integral from 0 to infinity for the infinite horizon problem of x squared plus u squared, okay? And the case that I will allow are the ones that stabilize the system, right? We have x dot is negative kx, because that was u. Then I want k to be negative, k to be positive, I'm sorry, because I'm using negative feedback. If we evaluate this integral, you get that the loss function looks like this. And in particular, its minimum value is 1, which is achieved at the point k equals 1. So that's all very classical. But one also very classical thing that people do is to ask the question, suppose that we want to minimize L without actually having access to the system. So here we had that A was 1, and B was 1, and Q was 1, and R was 1 in our LQR problem. But suppose that I don't know that. I just want to minimize this function, okay? That comes from this problem. And I'll explain why this is important later in what is called reinforcement learning. So, well, I'll mention it, maybe not explain too much. What we do this, many different ways, but the simplest thing that you can do is to look at a gradient flow. So you go in the direction of steepest descent of L, of the loss function. So you set the differential equation k dot is equal to negative gradient of L, all right? With k in this open set D. And of course, you can do more general things. You can look at Newton methods or projected gradients, so forth, and proximal gradient and so forth. And I'll let Leilei will talk a little bit more about that at the end. Now, if we look at the Euler discretization of the gradient flow, then of course we have the standard steepest descent iteration where there's some learning rate h, which is the step in the Euler discretization. So the question we're going to ask is, what do we know about convergence of L to its minimum value, or maybe of K itself, the feedback in the example, in general, some sort of parameter that we're interested in, to the value that minimizes. Please feel free to interrupt. I don't see your pictures, so you have to speak out because I minimize the pictures. But sorry, I'm having a problem with my screen. Why is this not? Sorry, why is this? Okay. All right. So, and so as I was saying, if you have any questions, please do just speak out, and I'd rather answer as we go if something is not clear. All right. So let me let script L of t be the relative loss along the solutions of the gradient system. So the difference between L of k and its minimum value L bar. That's obviously a non-negative number. Then because k dot is negative gradient, L dot is going to be the partial of L with respect to k, that is to say the gradient of L times k dot. K dot is negative gradient. There's some transposes in there because I'm taking gradients to be row vectors. In any case, L dot is going to be negative the gradient squared. And clearly that's non-negative. So the relative loss always decreases. And in fact, one can easily see, this is totally standard, that the pre-compact trajectories will always approach the set of critical points, that is to say the places at which the gradient is zero. One can actually show in the case of analytic loss functions that omega limit sets, which of course are included in the critical set, are actually single equilibria. So you can have interesting non-trivial omega limit sets. It's a theorem of Lukasiewicz for the analytic case. It's not true in C infinity. And in fact, one can prove that generically pre-compact trajectories converge to those critical points which are not strict saddles. By a strict saddle, I mean a point at which the gradient system has an eigenvalue with real part bigger than zero, which is equivalent to saying that the Hessian has a negative eigenvalue, really negative eigenvalue. So the general picture that we have, and this is interesting in different contexts here, the target set would be just 1 point, most of the applications that we do. But the general picture for gradient systems is at least you have analyticity of the loss function L, is if we know that every critical point, which is not a minimum, the T means target, right? The minimum. If we know that every critical point that is not a minimum is a strict saddle, then and if we know trajectories are pre-compact, then except for a set of measures zero, we converge to points in TC. So no matter where we start, we converge to the target set, okay? Except for a set of measures zero, like stable manifolds or center stable manifolds of the critical points that are not, of the saddles. This is actually a not 100% trivial fact in the case where you have continuous sets of equilibria, but it's by now fairly well established. And we had a paper with Arthur, who's here in the audience, in the last CDC, where we have a lemma in an appendix where this is shown, and it generalizes some ideas in the computer science literature. So let me remind you about something else that, again, some people in this audience may not be totally familiar with. We had that, of course, L dot is negative the gradient of L squared. Okay, now this is going to be the critical point of the lecture in some sense, no pun intended with the word critical. So let's make absolutely sure that everybody is on board, okay? So what we know is for the relative loss, we look at the solutions of the gradient system. We know that the derivative of the loss is negative the square of the gradient, okay? Evaluated along the given solution. Now, suppose that we have what is typically called the Pauli-Lukasiewicz inequality. So we have this inequality, okay? Meaning, and what I mean by that is that there is some positive lambda, so that there is the so-called gradient dominance condition, which says that the gradient square is bigger or equal than lambda times the relative loss. Or the way that I prefer to write it, for reasons that will be clear very soon, I prefer to write it in this form. I take square roots. Okay, that's not the way people usually write it, but you'll see why that's important. Now, clearly, if I have this property, and if I have that L dot is negative this guy, then of course negative of this is less or equal negative of that, right? Okay, let's do a negative of that. This was a relative loss. So what do we conclude? We conclude that L dot is less or equal than negative lambda L. So we have global exponential converges to zero of the relative loss, okay? Is this okay? I haven't heard anybody saying anything. And again, I'm not looking at the screens, the pictures. Can somebody say if it's okay? Are there any questions? Is anybody there?
It's okay, Eduardo. This is Bahram.
Hey, Bahram. Hi.
I can hear you nicely and everything clear. Thank you.
Okay. All right. So the point is that this is very nice when it happens, but sometimes we do not have this global convergence. And this is sort of what leads to what I'm talking about here. So usually, in many, many problems at least, such as the LQR problem that I was talking about, we only have some sort of semi-global PLI, polyallocative chain inequality. And what I mean by that is that the estimates that we have depend on the compact set on which you start. This looks like a really, trivial thing to worry about, but we'll see why it's important. So typically what we know is that for every compact set C, there exists a lambda that depends on C where this inequality holds. And therefore, if we start in that compact, or maybe assume the compact is forward invariant for simplicity, we have a nice exponential rate of convergence. However, as we take compact sets that are bigger and bigger in the domain of interest, for example, in the serval feedback stabilizers for a given system, that constant might be going to zero as we approach the boundary, right? So typically we may have an exponential rate of convergence on one compact set, let's say C1, a different rate of convergence C2, but as C2 gets closer and closer to filling all of D, it could be that this rate goes to zero. So, and in fact, this is what happens in the continuous time linear quadratic regulator policy optimization flow that I gave us an example a minute ago. So what I want to talk is this is the motivation. I want to talk a little bit about what we do in that case. And then, of course, ask a little bit about what about if instead of a linear comparison, we have some sort of nonlinear comparison functions, and also get into, of course, questions of ISS, since that's the name of the seminar.
Eduardo?
Yes.
It's Daniel here. Can I ask you a quick question?
You already did, but you can ask another one.
You did not mention Riccati equation anywhere.
I did not, on purpose. So the reason is that, and I think I have a slide coming up on this anyway, but the reason is that in the context, but let me just talk about the philosophy of this. So in the context of linear quadratic regulator problems, for example, but let's say we think of it as a reinforcement learning problem. Typically, we may not know the plant, so we don't know A and B. We may not even know the cost. We don't know Q and R, but somehow we try a control law and see how it works. So I'll talk more about this later. I'll have a little diagram explaining, but the idea would be there's some sort of oracle that evaluates how good your feedback law is and tells you the value of the loss, or I will assume the value of the gradient of the loss. Is that okay? So
okay.
Now, but just to make it clear, in order to analyze, the analysis that will follow will actually use the Riccati equation to be able to do the analysis, to say, okay, if this is what I know about the true solution, what is the regret of using this kind of direct method? Is that okay, Daniel?
Yeah, that makes sense. Makes sense. Thank you.
Okay. All right. So in that simple example, I realize I'm speaking slower than usual. In that simple example, you can actually see that I told you what the loss function looks like. And one thing that you can see is that, in fact, the loss function itself, the relative loss, goes to infinity as the feedback matrix either goes to 0 to infinity in the high gain limit. On the other hand, the square of the loss of the gradient is bounded as k goes to infinity. That's easy to see just by looking at this example when k goes to infinity, which means that it's impossible to have an estimate like this with any k infinity functions, and certainly not with a square root as in the case of the PLI inequality, because if this thing is bounded, right, and this thing is going to infinity, if alpha would be class k infinity, that would be a contradiction, okay? As a matter of fact, we can always see in this case, you can also see in this case that for large initial conditions, L dot looks like -1/4, right? I mean, that's just look at this, right? Okay, so what we're going to see is that L dot is actually just basically constant, so we only have linear decrease, we don't have exponential decrease. Although on each compact set, we certainly have exponential decrease. That's not a problem, okay? Okay, so, and this is just some plots to illustrate. Let me not go over the details, but you can see how this is two different initial conditions, and you see how you get something that looks like a very linear decrease until it switches to something that is more obviously exponential. And this is for a smaller initial conditions where the switch to exponential occurs before. Of course, this is not quite right. It's always sort of exponential or any compact, but it's just, and sort of, I can explain that more in discussion time, maybe one. But anyway, but that's the picture, that we have some sort of globally linear convergence, but locally exponential convergence. Okay, so the question is now, what can we say a little bit more generally? But before that, let me just point out something that is really confusing. In the flow, the same flow, okay, the gradient flow, but for a discrete time LQR problem, in fact, there is a global PLI condition. One has exponential global stability of the system. And this was a little bit weird. And it turns out that when you actually look, under the hood at what's happening is it's better understood with, say, an Euler discretization. If you do an Euler discretization, you look at the corresponding discrete time system for the Euler discretized dynamics, you'll end up basically with the property that you have an estimate. Let me jump to the actual estimate. You end up with an estimate like this, where this guy, okay, is still class K infinity. In fact, it's even a PL type estimate, but the H that appears in here, okay, goes to 0 as the sampling H goes to 0. In other words, as you approach better and better the continuous time system, this inequality basically breaks down. So that explains why, in my opinion, one way to understand why the discrete time problem is nicer, or at least why the discrete time problem could have a global property while the continuous time problem does not. So let me now talk about a little more general things. And as we said, the general Pauli-Lukasiewicz inequality was something like this, with alpha being square root of R, proportional to the square root of R. That gives you exponential convergence. So I'm going to talk now about a new class of functions that we defined. And we did this in the work with Leilei, and he's going to talk more about these things later. Suppose that alpha is not a linear function of the square root of R, but is a function of the form square root of A over B plus R. Okay, so the difference is if this thing would not be in the denominator, then of course you would have everything would be good, but this is a function, right, that will tend to saturate. Okay, so notice that for R near 0, basically this term doesn't matter, and we do have a Pauli-Lukasiewicz type inequality. That means that we'll have local exponential convergence. On the other hand, when R goes to infinity, basically we're going to have something that looks like just a constant, right? When R goes to infinity, you're going to get something, that term, right? So you'll get basically the square root of A, which is a constant. So that says that as R goes to infinity, basically we're only going to be able to say that the gradient decreases linearly, which is what I told you in the example. For those of you that know the famous paper of Polyak in 2021, it's subtly but importantly very different because of that square in the denominator. I can talk about that later if somebody's interested. But that changes the problem. That changes everything completely. Now, in this audience, I don't need to tell you that it's more interesting to look at, or at least in general for nonlinear systems, we want to look at comparison functions which are not necessarily linear, not necessarily square roots. So in general, we can look at positively definite comparison functions. Positive definite comparison functions. We can look at class K comparison functions. We can look at K infinity comparison functions. So suppose we do that, okay? And then we can think of the following general picture. We can talk about the global Pauli-Lukasiewicz inequality. We can talk about the semi-global Pauli-Lukasiewicz inequality. If we want, we can talk about local Pauli-Lukasiewicz inequality, where we only ask the semi-global thing to hold in one specific compact, and this saturated PLI condition that I just defined. And clearly, global PLI conditions imply a K infinity bound, because those are K infinity functions, right? A SAT PLI implies class K, right? Because the SAT PLI function, looks like this. It's bounded with class K. And semi-global PLI actually can be shown to imply positive definite comparison functions. So keep that in mind for a few minutes. And let me go back to the general LQR problem. In the general LQR problem, this is now what I was telling Daniel before, that we want to look at this problem as a problem in which we do not know A, B, Q, and R. but we want to understand the behavior of what's sometimes called a policy optimization, reinforcement learning policy optimization, which is to say, we somehow assume that somebody, an oracle, tells us what the cost function is, what the gradient of the cost function in our case is, and I should have called this L and not J, I'm sorry. Using some sort of other ways of finding out that, and I'll say a couple of words more about that in a few minutes. And this goes back a long time, Levine and Athens in 1970, so way over 55 years ago, people were looking at these kinds of questions, but not analyzing necessarily these convergence properties. Now, the problem is interesting because it's a highly non-convex problem, as I said. I think I'm going to skip this because otherwise I think that, in fact, Leilei will sort of talk a little bit about these things too. So the main result is the following. This is a theorem that we had in systems and control letters in this last year. And that's that in the case of the general linear quadratic regulator problem, sorry, typo. Okay. So the X should be outside of there, right? Okay. In the case of the linear quadratic regulator problem, the flow that you get is actually sub PLI, and you'll see in a few minutes why that is interesting. And therefore, it's also, of course, a class K type of estimate, but it is not PLI. Okay, as I showed you already with one example. There are a number of papers that are there in the literature showing basically semi-global PLI, okay, which would only give positive definiteness of the comparison function. Again, this will be clear in a couple of minutes why this is important in the context of things like ISS. Okay, so suppose that the gradient is imprecisely known due to either, basically we have an algorithm that does the gradient descent. In that algorithm, we're going to query, given an X, or K, okay, maybe I should call it K, we're going to query some sort of oracle or digital twin or computing subsystems or some system that is going to estimate for us the gradient, but maybe the gradient is corrupted by some sort of error or noise that could come from some adversary changing our estimate, or errors in evaluation by the oracle, or early stopping of a simulation. For example, it could be that this system right here is simulating, maybe you have a car and you actually run the car and see if the car crashes or not. And based on that, you decide what the value is of this particular feedback law, but you don't let the simulation go to the end. The car is approaching, the wall, and you stop it right there or something. So you don't have an actual exact value for the gradient of the cost or the gradient of the cost, but you have some estimate. Or it could be because in computer science, people talk about reproducibility, which is if you and I run two different run algorithms in our computers, and we use some random number generator at some point, saying stochastic gradient descent, we may get slightly different results, and so forth. So how do I model this? I model this as the simplest model would be add a disturbance, right? Add a disturbance to the gradient system, okay? So this is what we're going to talk about. And then the question is, what can we say about this? Can we say anything interesting about this? So obviously, if I would think you can say anything interesting, I wouldn't be giving this talk. Anyway, so I don't need to tell people the definition of ISS in here, so an integral ISS, I think. Somebody corrects me if I have to. So I'm going to skip all that. And here is the main result. So the main result is the following. Suppose that we have a K-infinity comparison, okay, between the gradient and the function. Suppose we have a K-infinity comparison between the gradient and the function. Then we have input to state stability of the system. So that holds, for example, for the discrete time linear quadratic regulator problem flow. Suppose, on the other hand, that we only have a class K estimate, okay? Then all we can conclude is small input ISS, which Leilei will talk about, and it means basically that for some bound on inputs, but not for arbitrarily large inputs, we have an ISS estimate. And if we only have a positive definite estimate, then we only get integral ISS. And of course, if there's a global probability of Hasiewicz inequality, therefore, since we have a K-infinity function of ISS, if there's SAT PLI, there's a, that's in particular class case, we have small input ISS, and that's really the new result in the 2024 paper for the LQR problem. And if we have semi-global PLI, which is all that was known in the past, you only get integral input to state stability. Okay, and of course the proof is, as you would imagine, you use L itself as an ISS or integral ISS Lyapunov function. I mean, it's easy to see that it's proper. It's coercive. There's some little details that I think for this audience, I'm not going to talk about that for this audience might be of interest, which is you really need to study ISS or integral ISS on an open set. So the question is, what is a good definition of that? Because, what is even properness, right? So basically what you do is you need to ask, what properness means, of course, is that the preimages of compacts are compacts. And one way that I like to define this, and I'm not the first one that came up, I just came up with this name, but people have called this indicator functions, Prali and Thiel in particular. But basically what you ask is that you have an ISS kind of estimate, but in terms of what is called what I call the size function, which is a function that is basically proper with respect to the target set that you're interested in. And you can always find such functions, and you can compare them to a class K infinity function. This is in a paper I wrote in 2022 or 2023 in Systems and Control Letters. In that paper, I had a mistake. I was claiming the LQR problem was ISS, and my mistake was because that was really true for the discrete time problem, but in the continuous time problem, it's not true. And that's what motivated then the later work with Leilei and Champagne to prove this small input ISS. So so I don't think I need to say much about this. So let me just conclude my part of the talk by saying that the theorem with Leilei and Champagne shows that the gradient system is small input ISS in the case of the LQR problem. Okay, and I'll let Leilei take over for now, and maybe we should leave the questions for the end. Is that okay? So I'm going to stop the share.
Great. Maybe I'll share my screen and talk about dive into the details of small disturbance or small input ISS. Yeah. Okay. So can you see my screen now?
Yes, we can.
Okay. So I'll go ahead and yeah. So firstly, maybe I should introduce myself again. So I'm Leilei. Now I'm a postdoc at MIT under the supervision of Professor Richard Brett. And before that, I got my PhD in New York University under the guidance of Professor Zhongping Jiang. And today I'm very happy here to follow Professor Sontag's talk and talk about the result on the small input ISS and its applications to robustness analysis of perturbed gradient flow. Usually for optimization problem, as Professor Sontag mentioned, for optimization problem, it usually operates or it is optimized over some open set. So a measurable set is usually not necessarily a Euclidean space. So we should choose a size function to decide how large, how far away from the equilibrium or from the optimum. So the size function should be, firstly, it should be continuous, and secondly, it should be positive definite. And finally, it should be unbounded or it should be coercive, which means that when the state tends to the boundary of our open set or tends to infinite, our value of the size function should be tends to infinite. Okay, so that's why we should use the size function to describe the behavior of a dynamical system. So here I also wanted to mention that this target set, like for a gradient system, this target set is a stationary point. But for any like a general nonlinear dynamical system, this target point is usually an invariant set for unforced dynamical system. So I will recall you like the definition of ISS, which means like it tells us that the trajectory of the state would tend to the neighborhood of this invariant set, and the size of this neighborhood depends on the magnitude of the noise, right? The U is our noise. But usually this ISS is it holds for any initial condition and for any arbitrary input U. But finally, for some dynamical system, for example, the policy iteration algorithm or the policy optimization of LQR, the researchers found that this kind of dynamical system can't tolerate any arbitrary inputs. It can only tolerate some small inputs, which means that ISS only holds for some small inputs. So that's why the researchers wanted to explore the concept of small inputs ISS to analyze the robustness of dynamical system. So what is the what is the small input ISS? So formally, the only difference between small input ISS and ISS is how small should the noise be, right? So here we give a threshold which is named D. So which means that if the input is smaller than D, the ISS property still holds. Since the noise input is smaller than D, so here the Gaon function just should be designed from 0 to D. So this is a slight difference between the classic ISS. And I wanted to mention that if D is equal to infinite, so we can say this is actually indeed the ISS definition, which means that this system can tolerate any arbitrary input. So that's the idea between ISS and small input ISS. So for ISS, we have a good ISS Lyapunov characterization. It tells us if V is a Lyapunov function, it is a size function. And then for any size of the state which is larger compared to the noise, the derivative of our Lyapunov function should be negative definite, right? But for the small input ISS, its Lyapunov function is slightly different. But still, we should use the size function to for the Lyapunov function. And secondly, we should say that if the input is smaller than some k function of the size of state, then the derivative of the Lyapunov function should be negative definite. So the only difference is that for the ISS definition, theta should be a k-infinity function. But for the small input ISS, theta should be a class K function. So for a class K function, it may be saturated. If there are some saturations for the class K function theta, so the disturbance U must be smaller than the saturation, such that this inequality can hold, right? So that's this equality also tells us that how small should the input be. Okay, so how can we prove the equivalence between small input ISS and small input ISS Lyapunov function? Okay, so the sufficiency follows directly from the idea of classic ISS. So for any bounded noise smaller than D, we can draw a compact set. And within this compact set, we find that trajectory will stay there all the time, which means that this compact set is invariant. But when the trajectory is outside this compact set, the derivative of the Lyapunov function is a negative definite. So by the comparison lemma, we find that it will approaching this compact set, and afterwards it will stay there all the time. So that's the whole idea of sufficiency proof. So next I will talk about the sketch of the proof for the necessity. So for necessity, we introduce a diffeomorphism between an open ball and a Euclidean space, which is phi. So phi is a diffeomorphism. We find that for any input U, we can reparameterize it by some vector in the Euclidean space V, which means that for any bounded input U, we can reparameterize it maybe by some unbounded value V. So if we consider V as the noise, as the input for this dynamical system, we find that if the original system is small input ISS, after the reparameterization, the dynamical system is the ISS. So if the dynamical system is ISS with respect to the input V, so we can always write down the ISS Lyapunov function, right? As I mentioned in the last slide. So the noise V should be smaller than some, if the noise V is smaller than some like K infinity function of the optimal function, we can say that the derivative of the optimal function should be negative definite. Okay, but there is and I mentioned there is a relation between U and V, right? If V, the norm of V is smaller than this one, we can see that the norm of mu is smaller than this one. So here we should introduce the theta one. Theta one can be directly can be directly derived from this equation, and we find that theta one actually indeed it is a class K function, but not of a class K infinity function. It is 0 at 0, strictly increasing, but saturated but it is saturated when R tends to infinity. So which means that this is exact the a small input ISS the optimal function for the dynamical system, and therefore V is a small input ISS the optimal function. And we show the necessity of the optimal as small input ISS the optimal function. Okay, so that's the whole idea of small input ISS. So next I will dive into the details of policy optimization for LQR problem. So as mentioned by Professor Sontag, so usually for policy optimization for LQR, our system is a linear system, and our controller is a linear feedback controller, which is parameterized by K. And for the LQR case, we want to optimize over K, such as the quadratic cost integral of the quadratic cost is minimized. And by utilizing the Lyapunov equation, we can directly say that the loss function for LQR actually indeed is a trace of the cost matrix. And this cost matrix can be calculated by showing this Lyapunov equation. Of course, for LQR problem, we will always the admissible set should be all the stabilizing controller, right? So here K should be all the feedback gains such as A minus BK is a Bohr weight. So from perspective of reinforcement learning, this equation actually evaluates the performance of the controller. It tells us how good the controller K is. And as we know, if we know matrices, if we know system matrices A and B, so we directly can calculate the optimal feedback controller K by showing this Riccati equation. So here I slightly rewriting the Riccati equation such that it is more consistent with the Lyapunov equation. So we find that the solution of the Riccati equation, which is pi, which it is the exact the cost function of the optimal feedback gain. Okay, so these two equations are consistent. Okay. Then due to the unknown system model, maybe we should use some, as mentioned by Sontag, so we should use the policy gradient algorithm to find the optimal controller. So the the gradient of the LQR loss can be calculated by taking the here PK is the implicit function of K, right? So we can utilize some calculus of implicit function and get the gradient of the loss function. And we find that in order to compute the gradient, the YK, we should compute YK, which is the solution of another Lyapunov equation. So usually we can't implement gradient descent algorithm exactly. There are always some external noise U. So our aim is to show that this kind of class K PL condition is satisfied. So here alpha is a class K function. If this kind of condition is satisfied, based on Professor Sontag's talk, we can show that the perturb gradient flow is indeed a small input ISS. Okay. So now let's go to the proof of proof of this statement. So let's look at the expression of the gradient. Expression of gradient is composed of two terms. The first term is the YK. The second term is the K minus K prime. So prime is equal to B transpose PK. Okay. So we may be curious about how large YK is and how small YK is, right? So the first is what is the lower bound of YK? because yk is usually a matrix, so we should use some like smallest eigenvalue to describe this like lower bound. And after some derivations, we find that yk is lower bounded by this value. And we find that if k tends to infinite, and its lower bound would tend to 0, because this is a fraction of the norm of k, right? And another question is how large yk is. So yk, we find that yk is upper bound, can be upper bounded by the LQR loss function. So that's another upper bound. And to illustrate this lower bound and upper bound, we use a scalar system. And for scalar system, a minus bk is directly a scalar, right? We can directly calculate yk by dividing a minus bk from both sides of the equation and find that this is the expression of yk. And after some like very simple algebra, we find that for scalar case, the lower bound is exactly the same as our derived lower bound for yk, right? So here bk minus k optimal, and here is like we use Frobenius norm if k is like for multiple input systems. Okay, and for the scalar system, we can also explicitly write down the expression of pk. So here it is the expression of pk by dividing like a minus bk from both sides of the equation. So this is a like expression of pk, and we see that pk is lower bounded by yk is upper bounded by pk divided by q. So that's the whole idea. Like that's the illustration example of LQR of yk, like lower bound and upper bound of yk. Okay. The next property is some geometric property of the LQR loss function. So in this slide, I want to show you that indeed LQR loss function can be interpreted as a quadratic distance over the Riemannian metric. So here Riemannian metric means that for any stabilizing, for any point in this set or in this like a Riemannian manifold, we assign a Riemannian metric yk. But for usually like for if k is in the Euclidean space, we use the Euclidean metric for all the point k. But if we use the Riemannian metric for different point, we have different metric yk. Okay, so we find that if we consider the distance between k and k bar over the Riemannian metric yk, we find that LQR loss is exact the quadratic function or quadratic distance of k between k and k optimal. So that's a very interesting geometric interpretation of the LQR loss. Okay, so if we consider the distance from over another Riemannian metric, which is assigned to the k optimal, we find another interesting property, which is the LQR loss function can be interpreted as the distance, as the difference between two quadratic distances. So the first distance is between k and k prime, and the other distance is between k prime and k optimal. So this we find from this equation, we find that indeed the distance between k and k prime is actually very large, right? And by utilizing some techniques like Cauchy-Schwarz inequality and Young's inequality, we can find that the Euclidean distance between k and k prime is larger compared with the LQR loss and the distance between k and k optimal. That's another interesting geometric interpretation of LQR loss. Okay, so given these different kinds of properties of LQR loss, so now we can derive the PL class K PL condition for the LQR loss. So recall that the gradient of LQR loss is composed of k minus k prime and yk, right? So here we should take the Frobenius norm of the gradient, and we find that its square of the square norm of gradient is equal to this one. So it is a quadratic function of k minus k prime, but over the Riemannian metric of yk square. Considering the lower bound of k minus k prime and the lower bound of yk we discussed previously, we can directly write down this equation. this one is the lower bound of K minus K prime, and the other one, this one, is the lower bound of YK. So here it is. Yeah. Okay. So now we find that this function sigma is a two-variable function, but for PL condition, it should be a function of only a function of loss of L, but not K, right? We should eliminate. Our goal is to eliminate K from this lower bound. Okay. So we find that for any fixed L, if we're increasing the norm of K, we find that this value of sigma is first decreasing and then increasing. So this phenomenon can be directly obtained by taking the derivative of this sigma with respect to the norm of K. And we find that one norm of K is equal to some constant, some proportional function of the loss function. Sigma reaches the minimum, and we plug this equation into the expression of K minus K optimal, and we get the lower bound of the gradient, lower bound of the Frobenius norm of gradient. And so here we find that indeed this function is exactly what we want, right? It is 0 at 0, strictly increasing, and it is saturated when my loss function tends to infinite. So that's the whole idea of proving the class K PL condition. This is previously we mentioned gradient flow, but this is the gradient, and usually we find that for this gradient we find that okay. So for the scalar case, which means that A, B, Q, R are all equal to 1, we find that here is a stationary point, and at the left-hand side of the at the left-hand side of the stationary point, we find that the gradient is so large, but at the right-hand side, we find that it is even saturated. So this is left-hand side is large, right-hand side is saturated. So this is a non-isotropic property of the gradient. And why this kind of non-isotropic property happens? It is because of the YK. We find that YK tends to infinite when it's when the K is very close to the boundary of our admissible set, but tends to 0 when K tends to infinite. So over the Riemannian metric, over the Riemannian manifold, so we can take the Riemannian natural gradient of the loss function, and we find that if we're taking the gradient over the Riemannian metric, we find that is the YK disappears, right? So our aim too is so that the perturbed natural gradient flow is also small input ISS. Okay. So the natural choice of Lyapunov candidate function is the loss function. So when we're taking the derivative of the loss function, right, and plugging in the natural gradient flow into it, and using the lower bound of K minus K prime and lower bound of YK, we just obtained in the previous several slides. We find that for this equation, it's very hard for us to decide whether loss function is a candidate is a small input ISS function or not. Why? Because we can see that 1K tends to infinite. The coefficient of L here may tend to 0, right? But for the noise term, we find that its coefficient is constant. If so, if even some small noise would destabilize the dynamical system. So now we didn't get the small input ISS Lyapunov function, and we should introduce another function. So we introduce a quadratic distance between K and K optimal and another Lyapunov candidate, and we're taking the derivative of it, and we find that it has some good structure. It is a minus, here is the noise term. I want to say that to get the last equation, we should introduce another geometric property of the LQR loss, which means that the inner product between K and K prime and K and K optimal is equal to the LQR loss and the quadratic distance between K and K optimal. Okay, And when we introduce, so finally we find the candidate Lyapunov function, which is should be the loss function plus the quadratic distance between k and k optimal. And this is like derivative of our Lyapunov function. And for this function, we find that if input is smaller than this value, we can say that our gradient descent algorithm is the derivative of our Lyapunov function is a negative definite. So indeed, this function is a k function of V, and therefore we say that based on our previous results on small input ISS, we say that the part of the natural gradient flow is also small input ISS. Okay, so I also wanted to introduce another kind of gradient descent algorithm, which is Newton's gradient descent method. So we can write down the second order approximation of the LQR function, and we find this is the second order approximation, and near the optimal solution, this term is equal to 0, and it is negligible, and we can directly approximate find the second order approximation by this first 3 terms. And by taking the minimization over epsilon, we find the Newton cos-Newton gradient direction. And here, following the similar logic as the natural gradient descent algorithm, also prove that the perturbed Gaussian-Newton gradient flow is a small input ISS. Okay, so that's all my presentation about technical details on small input ISS and its applications to like a gradient flow. That's it. Thank you.